We'll be starting in 7 minutes. Okay. Shall we get started?
Go for it.
Hi, everybody. So let's see. I'm going to share my screen. Can you see the slides?
Yeah, see the Pluto notebook.
Okay. So, hi, everybody. So today we're going to talk about why we can't predict the weather, but we can actually predict the climate. So first of all, of course, we have to talk about, or we have to discuss, what is actually the difference between weather and climate. So we all know what weather means. I want to know, when the class finishes at 3 p.m., say, my time, is it going to be raining? Can I go for a walk? And, I can just go online and look up the weather, and there will be a prediction of what we expect to happen at 3 p.m. And I can actually be pretty sure that that will be accurate. We have data about where the rain is right now, where the clouds are, and we can actually predict how those clouds and rain are going to move, because we understand the dynamics of the masses of air and how water evaporates or forms clouds, etc. So these are all very complicated physical processes, but we actually understand them reasonably well, and we actually can put them in models, which are basically partial differential equations that tell us how air actually moves around. If given the wind speed right now, how is this bit of air going to move, and then how will that wind change later? We can actually predict this quite well. And maybe we can even predict what will happen at 3 p.m. tomorrow. And if we're very lucky, we can predict what will happen at 3 p.m. in 1 week's time. But you certainly would not expect to be able to predict correctly what will happen at 3 p.m. in 1 month, and certainly not in 1 year. On the other hand, we can say, the average temperature in Boston is somewhere around 55 degrees Fahrenheit, or that's something like 12 degrees Celsius. And that's going to be, I can be pretty sure that next year it'll still be around that much. And the following year, it'll still be around that much. On the other hand, in 100 years, I'm not actually sure, because we have climate change, which is a gradual change in the average temperature. So climate is basically somehow the average weather. And then weather is this sort of short-term, fluctuating situation that depends on very local conditions, whereas climate, we're averaging over, over all of the days in March or April, and then it becomes suddenly much more predictable. And so, the goal of today's notebook is going to be to understand, well, so we're not actually going to model the weather, really. We're going to end up with the sort of simplest possible model of the atmosphere, which is a system called the Lorentz Equations that many people may have seen before. We're going to build up to that to understand, if we have some model of a sort of physical process or a scientific process, what kinds of behavior can we actually expect it to have? So we're going to start off by looking at, we'll only be looking at ordinary differential equations today, and we'll ask what kind of behavior can they have sort of in the long time.
And if I could just interject probably a small point, it seems many people believe that climate models are these big complicated things, and well, they are big complicated things, but that doesn't mean that one can't get a feel for them fairly early in a university career, for example, as an undergraduate, for example, that you can get a good sense as to what's going on in climate models. And so, given how important they are for all of us, we thought we would spend some time on some of the aspects of climate modeling.
Yeah, so we'll actually start off with some simple climate models, which basically, next time maybe, which basically tell you something like, what is the average temperature over the whole Earth, and how does that change in time? And it changes because there's a sun out there that's warming up the Earth, but then you lose energy as well. And so you can make sort of very, very global models in a much more simple way. Whereas if you actually then want to really specify how do things change over the surface of the Earth, that's going to be much more complicated.
And the cool thing is that not only do you learn about climate models, kind of, whether probably most of us will never go into climate modeling, but you learn a little bit about it as it affects us all. And in any event, the things that you will learn apply in so many other areas of modeling anyway that, it serves as an example.
Yes, exactly. So today we're going to start with that process. So we'll look at, and so actually what we're sort of really looking at is this subject that some people call nonlinear dynamics or dynamical systems, where we take an ordinary differential equation and instead of trying to really, study exactly what each trajectory does if you start at a particular initial condition, well, we're trying to get a more global qualitative picture and say what kinds of behavior can we find? What kinds of things can the system end up doing? And so we'll look at, in particular, stability and bifurcation. So we'll see what that means. Okay, so our models are all going to be ordinary differential equations. So we've already had a couple of lectures on this. We saw last time how to use the Differential Equations JL package to solve these, and I'll be using that to solve the more complicated equations in this notebook. And so let's remind ourselves what that means. It tells us if I'm at a current state, how I'm going to change as I move forward in time from that state. And if I move forward a little bit, then the state changes. And so actually the direction I need to move changes as well. And so when we kind of add up all those little changes, we end up with some trajectory that moves forward and changes in some way in time. And that's what we're trying to calculate. So we saw that this forward Euler method is this very simple algorithm for doing that, for us doing time stepping, advancing in time step by step with these time steps of size size h, which is we're thinking of as being small. But we also said last time that this method, although it's sort of very intuitive and easy to derive, is actually not a very good method for actually solving differential equations. And so we can use this package that has these much better methods implemented already. Okay, so let's start off with a very simple model in one dimension. So we only have one variable that's changing in time. So we'll call the variable x. And again, x dot, as usual, is the time derivative, the rate of change of x in time. And x is going to be the population of bacteria, the number of bacteria in some dish as time goes on. So how is that going to change? It's going to go, or what affects how that bacterial population grows. So if there's a lot of food available, then we know that bacteria will just sort of reproduce at some rate. And so we'll basically get exponential growth like we've been studying before. We studied exponential decay, but you get exponential growth modeled by this x dot equals lambda times x. So lambda is the growth rate, basically how many sort of offspring each bacterium will have in a given time. But if the bacteria is limited to some kind of petri dish, there's only a finite amount of food. And so you cannot expect the bacteria to just keep on growing and growing, because they'll sort of eventually overwhelm the whole world. Instead, what will happen is there's a sort of maximum number of bacteria that can exist on this plate, which is called the carrying capacity. And that's often written as this capital K. And so we're going to model that competition of this exponential growth and this saturation due to having only a possible finite number of bacteria in the dish with this term K minus X. So basically, if X, the population of bacteria, is bigger than K, then this will be a negative number. And so the rate, and so the change in X will be negative. The derivative will be negative, and so X will have to decrease because there's overcrowding. So there's competition between these two effects, and we can just simulate this equation to see what that gives rise to. By the way, this for some reason, this equation has the name logistic differential equation, and I've never quite worked out why it's called logistic, and that name does not seem to be at all useful to actually think about what it's doing. So let's just call it the sort of bacterial growth equation. Okay, so so it turns out that by changing the variables, we can get rid of all these annoying constants, the lambda and the k. So I say how to do that here, and you get down to this simpler version of the equation. So x dot equals x, that's the exponential growth, times 1 minus x. So basically x is sort of now the proportion relative to the carrying capacity. So when x is 1, that means we're at the capacity of the system. And so, we can use differential equations .jl, or I wrote my own little Euler routine, which is at the bottom of the notebook. It's this kind of the same idea. So here's the logistic, the right-hand side of the logistic differential equation, x times 1 minus x, and then we're just integrating it using some method, numerical method, you're starting with some initial value with a step size and a final time. Okay, so what actually happens? So I've been having a little bit of trouble with my figures being different sizes and things. Sorry about that. So let's see if we just remove this. Is that going to be better now? No. Okay. Anyway, well, I can just zoom out now again like this. Okay, so what happens if we start at time 0 at height, basically population 0.5? Well, the population initially increases. It seems to be increasing something like linearly right now instead of exponentially, because there's this competition. It already has a pretty big value. So it's going to increase in some way, and then it'll saturate. So it converges to 1.0, and then it just stays there forever. And if I carry on integrating for a longer time, it'll just stay. And so that's one of the possible behaviors that a differential equation can have. It can reach a value and then stay at that value. And such a value is called a fixed point. Because if I start there, I'm fixed. I don't move. Okay, so let's see what happens for other initial conditions. So let's here's an interactive visualization using the usual tools. What if I start very close to 0? Well, I see that actually, oh yeah, there I see that there's something that looks like exponential growth, and I could go and plot this on a semi-logarithmic plot to see that actually whether that is exponential growth initially or not. But
Dave, could I ask a quick question on the previous curve? How hard would it be, not this one, but the one just before, would it be for you to start at time minus 20 and start close to 0?
I mean, that's what I'm doing here, right?
Yeah, I guess that is what you were doing there. What I was hoping is for it to look a lot more like the sigmoid curves that we always see in machine learning, since I think students are interested in that.
I can just let's.
What would it take to make it look like that?
Let's make it go up to time 10, something like that.
Yeah, it'd be nice if it looked symmetric, but we don't have to go crazy today.
I mean, it doesn't, physically, it doesn't make much sense to take negative time, right? I'm starting at a given time.
Yeah, it doesn't matter, right? This is time independent anyway. So, right, it's whatever they call it. There's a word for that in differential equation.
Okay, yeah, it's autonomous.
Autonomous is the word.
Autonomous.
This is an autonomous equation. But the question is to make it look like, and the key point is, of course, that if you're doing, I mean, some folks will be familiar with machine learning, others won't. But if you're doing gradient descent, the fact that the derivative is so nice plays an important role.
Okay, so there you are. That looks like a sigmoid.
It's getting there.
Yeah, so
I'll take it.
So if we're starting, very, very close to 0, what happens? We move away from 0. We have this kind of exponential looking growth. But then once we get to, 0.5 or something, this other effect takes over. There's this competition, and we just converge again to this fixed point at 1. And so it looks like the dynamics is pretty boring. Everything is going to converge to 1. So let's just keep on going closer and closer to 0. What happens if we start exactly at, so this is now 0.001, the initial condition, and you see that it sort of stays close to 0 for a long time, but then it does sort of lift off and moves to 1 in the end. But what happens if we start exactly at 0? So if we look at the differential equation, if we have a 0 in here, then we get 0 times something, which gives me 0. And so the derivative is going to be 0. And so if I start exactly at 0, then the derivative is also 0. And so I'm not going to move away from 0. And the same thing is actually going to happen at 1. And so 0 is actually another fixed point. So let's see that. If I start exactly at 0, I just stay at 0. And also we can see that at 1, if I start exactly at 1, I stay at 1. Well, okay, you can guess that that's true. What about if I start above 1, I'm overcrowded, and so the population decreases and still converges to 1, right? So it looks like everything's converging to 1. But what happens if I start with a negative population? Of course, that doesn't make any sense, from a sort of physical or biological context, But it makes sense from the point of view of the differential equation. I can just ask what happens if the initial condition is negative. And you can see that what happens is it just sort of zooms off in the negative direction. So it moves away from 0 again. So let's summarize all of these trajectories in one single plot. So these are all the different trajectories starting from all different initial conditions. So this is sort of like having an ensemble, a collection of different copies of this Petri dish, and starting with different amounts of bacteria in each one, and negative amounts of bacteria in some of them, whatever that means. And so what can we see? We see that indeed, if I start at 1, I stay at 1, and if I start close enough to 1, I get attracted to 1. But if I start at 0, I stay at 0, so 0 and 1 are both fixed points. But if I start close to 0, I actually move away from 0. And so we make a distinction between this fixed point, which is stable, and this 1 is stable, and 0 is an unstable fixed point. And so you can see that fixed points are sort of an interesting and useful kind of organizing feature of this set of dynamics. If I know that I have a fixed point, then I can look what happens close to that fixed point, and that actually sort of actually these fixed points in this one-dimensional system are actually separating different kinds of behavior. So if you're anywhere between 0 and 1, you converge to 1 from below. If you're anywhere above 1, you converge to 1 from above. And if you're anywhere below 0, you go away from 0 to minus infinity very fast. Okay. So here, to get that information, what did we do? We actually integrated the differential equation using one of these numerical methods. Could we actually get that information in a different way without actually integrating the equation? And the answer is yes. So in order to do that, we're going to think of what's called the state space of the system, the space of all possible states. So all possible states are just all real numbers between minus infinity and infinity. That's what the values that the system can take. And we're going to plot a vector field, so arrows that tell me in which direction am I going to move. That's all I'm going to plot. And that looks like this. So what does this plot mean? It means if I am at height 0.5, I calculate x dot, the rate of change of x, at 0.5, I get a positive number. And so I'm going to end up moving upwards if I start at that point. If I start at 0.75, I'll move upwards. If I start at 1.25, I'll move downwards. If I start exactly at 1, I'll stay at 1. And so this picture actually summarizes all of the dynamics of this system. And you can see that there are indeed sort of 3 regions of the real line. Anything, as I said before, anything above 1 will converge to 1. Anything between 0 and 1 will converge to 1 as well. And so you can see that these arrows pointing towards 1 mean that 1 is actually a stable fixed point. And the arrows, on the other hand, can go away from 0, and so 0 is an unstable fixed point. And so we actually got all of this information, which is the qualitative dynamics of the system, without ever really solving the differential equation. All we did was sort of look and see, oh, which direction am I going to move in? Okay, so this picture is called the phase portrait, or it has various names. So I'm drawing state space or phase space, and I'm saying what is the qualitative behavior of the system in that space. Okay, so these fixed points are special, and they satisfy an equation, which is that the derivative, if I start at a fixed point, has to be 0. And so that is, if my differential equation is x dot equals f of x, that means that a fixed point satisfies f of x equals 0. In other words, a fixed point is actually a root, or a root of the function f that defines my differential equation. So I can find those roots using, for example, the Newton method that we saw a few weeks ago. And to do that, I'm actually using a package in Julia called roots.jl. And that finds roots in 1 dimension. In the higher dimensional examples that we have later, I was actually going to use a package that I wrote called interval root finding, but then it turned out that to be a bit too complicated to fit into today's class. Maybe we'll look at it later. Okay, so now what can we do? We have this system, but this picture is actually a complete picture of all of the things that particular system can do. So let's look at a slightly more complicated system. So now what we're going to do is have a different equation. So we're going to look at this differential equation, x dot equals mu plus x squared. It's similar to the previous one. The previous one had a quadratic behavior. It had x times 1 minus x. Now we're just going to replace that x times 1 minus x by this x squared, but we're going to add mu. And mu is going to be a parameter that we can change. And we're going to see what happens to the dynamics, to that picture that I just drew, as we change mu. And so the answer is that it looks pretty similar to the previous case, right? It's just the sort of the other way around, actually. I have an unstable fixed point up here at 1 and a stable fixed point down here at -1 for this particular value of mu, which is -1. And now I'm going to change this value of mu bit by bit. And as I change it, we're going to watch what happens to this phase space and the qualitative dynamics. So as I change mu, what do we see? We see that the fixed points are actually moving closer to each other. And as they move closer to each other, but they're moving closer to each other, but the qualitative behavior of the system is still the same. There's still these three regions where you either converge, move up or down, and you converge to these fixed points. But what do you think is going to happen as I increase mu? When mu hits 0, what happens is that these fixed points actually collide with each other. And then for mu bigger than 0, we no longer have any fixed points. Why is that? Because mu plus x squared equals 0 is the equation of the fixed points. And you can see that when mu is, say, 1, I have x squared plus 1 equals 0. In other words, x is the square root of -1. And so that does not have any real solutions. And so basically, now you can see that the dynamics of the system has completely changed in a qualitative way. Now, wherever I start, I'm just going to move upwards. I'm just going to sort of carry on upwards until I get to infinity, right? So that I no longer have any fixed points. If this represented a physical system, instead of stopping somewhere, I now would just go off to infinity. So this is really a qualitative change. So at mu equals 0, there is this qualitative change in behavior, and I can see it right here on this as I move mu. And this is called a bifurcation. So bifurcation means something splitting in two. And so you can think of this as sort of splitting, the space of mu now. Now there's a sort of extra parameter, which is mu, that has been divided into two regions, one with one kind of behavior and one with another kind of behavior. And that's why it's called a bifurcation. And we can actually put all of those vector fields that I drew together into this picture. So now I'm drawing, in the vertical direction, I'm drawing exactly the same picture that I just drew with the unstable fixed point upstairs and the stable fixed point downstairs. But now I'm stacking them all together for different values of this parameter mu, so that we can see them all at once. And what we see is that this is now called the bifurcation diagram of this system, and we can see that indeed, if you fix your attention at a mu that's less than 0 and a mu that's bigger than 0, you can just immediately see that the qualitative dynamics is different because these fixed points have disappeared. And so, okay, yeah. So there's this critical value of mu, which in this case is 0.
Can you remind me how mu entered? I've kind of lost track.
What did you say?
How did mu fit into the story there?
Mu is in this differential equation.
Okay,
x dot equals mu plus x squared.
Got it. Okay.
So as we're changing mu, we're actually changing the differential equation, and that's like something like you have a pendulum and you're changing the mass or something. You're changing some parameter, some variable, if you like, of the physical system or the biological system. So we could be changing the rate at which bacteria reproduce, and then suddenly it turns out that it's no longer possible for the system to reach a stage where the bacteria have a fixed population. Okay, so now let's look at a slightly more complicated example. So we now have a cubic in my ordinary differential equation, a cubic expression, still with mu plus that, and we're going to do exactly the same thing. So we could go through and plot the vector field and then change mu interactively, but let's just jump in and look at the bifurcation diagram again. So this again represents, for each value of mu, if you fix a value of mu in this differential equation, then you're supposed to be thinking of taking a vertical slice through this diagram. So for example, if I take the slice when mu equals 1, what is the qualitative dynamics? Everything below this fixed point converges up to the fixed point, everything above it converges down. And so there's one single stable fixed point. And the same happens if mu is, say, -1. There's one single stable fixed point. Everything converges there. But what happens for this region of mu in between, say, -0.4 and 0.4 or something like that? What happens is something different. Now, there are 3 fixed points, right? That corresponds to the fact that we have a cubic equation that we're solving, and there might be up to 3 real roots. There's either 1 or 3 real roots, and we can see that in this picture. Over here, I only have 1 real root, and over here I have, in this region, I have 3 real roots when I take a cross-section, a vertical cross-section of this picture. And it turns out that one of them, this one in the middle, is unstable, whereas the other 2 are stable. So wherever I start, except if it's exactly at this unstable fixed point, I'll move away from that middle point and towards one of these 2 fixed points. And so basically, the dynamics is now quite different. We have what's called bistability. We have 2 fixed points that can exist and that attract a whole neighborhood of initial conditions, and they coexist. And so this is like a system which has 2 possible states in which it can be. And if I perturb the system away from those states, it will just come back to where it was. And so we'll see next time or soon that this is exactly what happens in one particular model of the climate of the Earth. Okay, so that's called bistability. And now what happens if we actually, so here's a picture of just the fixed points. And so you can see that we have what are called branches, these curves. Basically, these curves represent solutions of this equation. And again, sometimes we only have 1 solution for a given value of mu. Sometimes we have 3 solutions, and they connect up in this particular way. That's very characteristic of certain physical systems. In particular, what happens if I now vary mu slowly? If I vary mu slowly, what is going to happen? If I look at this picture again, if I'm up here, then the dynamics is actually forcing me down to towards this fixed point. And so I'm going to sort of very rapidly actually converge to this fixed point. And now if I increase mu gradually, what will happen? I'm going to increase mu. And so now if I increase mu by a bit instantaneously, I'll now actually be away from the new fixed point, which is a sort of stationary, stable behavior for that particular value of mu, but I'll very quickly actually come back to it. And so basically, as I move mu slowly along, my system, the position of my system will actually track this stable fixed point as I move mu. And that will continue to happen until I get to this critical value of mu, at which this fixed point actually stops existing and ceases to exist. And you can see from this vector field that now what's going to happen is it will very rapidly jump up, or not jump, but very rapidly sort of whoosh upwards, and it'll reach the other fixed point. And then if I carry on increasing mu, it'll track this branch. But if I decrease mu, it'll still track this branch. So it'll actually move along this value, well, this set of fixed points until I get again to this critical value, and then it'll jump back down here. And so you can see that the value of mu, or the value of the fixed point, which particular fixed point it is at, actually depends on the history, depends on where I came from. And this process is called hysteresis. And again, we'll see that it comes up in one of these models of the climate. And it kind of explains features of today's climate. Okay, so that's the kind of phenomena that can occur for one-dimensional dynamical systems, or ordinary differential equations. Now let's jump to 2 dimensions. So basically, we've just seen sort of all of the possible behaviors that you can have in 1 dimension, which is you either converge to a fixed point, or you converge to a different fixed point, or you might have an unstable fixed point where you go away from, or you can just go off to infinity. That's all you can do in 1 dimension. What about if I now have another variable? So we have a 2-dimensional system. So here we have an example, which is called the Brutalet Model, because it was developed in Brussels in the group of Ilya Prigogine, who won the Nobel Prize for Chemistry in 1977. And it's a model of a chemical reaction. So X and Y here are concentrations of chemical species in a particular reaction. It's a model of a reaction called the Belousov-Zhabotinsky reaction. And that reaction became famous in the sort of 50s and 60s because it actually oscillates in time. It's basically like a chemical clock. It will be in one particular, when you mix up these chemicals, it's sort of, you can look at this, I looked up this on YouTube. It's in one state which is red. It actually looks red for some amount of time, and then suddenly it all changes to blue. And then at some other time it changes back to red, and then it'll oscillate in a periodic and repeatable way. This is a model of that. So it just has these two variables, x and y, which are concentrations of two particular chemicals. But it has the property that x, this chemical modeled by x, is what's called autocatalytic. So basically, if you have enough x and it's reacting with itself, it will produce even more of the same x. And so the amount of x will increase over time. But it can only increase so much because, again, there's a competition and some other process destroys x. And so basically you sort of create a lot of x, but then you run out of enough x. And so the amount of x goes down. And then at some point it'll increase again because it tries to produce itself, and then it'll go down again. And that's how you end up with these oscillations. And so I'm using differential equations.jl now to solve this system. So here's the definition of the system, just like we did last time. It has parameters a and b. These a and b are parameters that will be able to change. And x is this vector of two variables, x and y. And then I just return the right-hand side of this differential equation, just like last time. So what does this actually do? Here's a picture of, again, the state space for the Brutalet model. But now the state space has two dimensions. So I can actually add labels. Right, so on the x-axis, we literally have the x variable, and on the y-axis, we have the y variable. And so there we go. So what are we seeing here? We're seeing trajectories starting from different initial conditions. So here, for example, I'm starting from 1,3, this point, and I'm going to follow this yellow or green trajectory around. This is representing the dynamics of the system in time. So I no longer see time, well, I didn't see time before either. This is the equivalent of that one-dimensional vector field that I had before. So these gray little lines are actually the direction field. So these are the directions at each point that I'm going to move in. So you can see that, over in this region, everything is sort of pointing southeast, and all the trajectories indeed move southeast. But then at some point around here, the direction in which they're supposed to move changes and pushes them back towards this point. And actually in here, there's one fixed point, and everything is being attracted in a spiral into that fixed point. Everything is spiraling into that fixed point. From the whole plane, everything just collapses into that fixed point. But now let me change this parameter b. And I'm having the same problem as Alan, that I can't actually change the parameter. So as I change the parameter, the behavior changes. And you can see that here, everything's spiraling into the fixed point. But as I increase b, so the fixed point moves, and the shape of these trajectories changes. And at some point, again, there's a bifurcation, and the qualitative behavior of the system changes. So here you can see that it's sort of trying to create I think it doesn't happen quite yet. Here, everything is sort of still spiraling in, but now we've reached a point where, if you look at this green trajectory, it starts here, I believe. It starts here, and it actually spirals out. And as it spirals out, it converges to this, this periodic orbit, in fact. So everything else is spiraling in, stuff from inside is spiraling out, and everything's converging to this loop. So there's a loop in this space where basically if I start at, say, I don't know, x equals 2 and y equals 1.5 or something, I start there and I'll go round, and I'll come back to exactly the same point, and then I'll just keep going round again, and I'll keep going round again. And that represents an oscillation in time. So I could draw, am I going to be able to do that? Not sure. not sure if I can actually draw the solutions in time that easily. I'd have to, the solutions in time basically are oscillating functions that look something like sine and cosine, but with a different shape. And so sine and cosine would be exactly circular on this plot. And this is something like sine and cosine, but oscillating.
Is the concern that you've got two variables now? I mean,
well, so each of the variables has an oscillating.
Something to guess, maybe I'm just dead wrong, but if you went like plot sol of one or whatever you called it in plot solution.
Yeah, well, the problem is I don't have the, maybe I do.
You do, SOLN, you have it right there.
Okay, yeah.
I think
a plot solution vars equals 1. Actually, no, just plot solution, I think will do it.
Probably would, yeah. You get both curves on one end.
Yeah, so there we go. We get both of the solutions. So you can see that they're sort of oscillating something like sine and cosine, but with a very different shape, actually. And that different shape corresponds to this different non-circular shape here. And so, yeah, thanks. So you can see that initially, when we're not periodic, it's not periodic, but then it settles down eventually to an exactly periodic shape, or converges to an exactly periodic shape. So over time, so time is moving on, increasing on the x-axis, and we're plotting x as a function of time and y as a function of time on the y-axis.
I think it's a good exercise to like see. Oh, let's see. The blue is roughly going from 0.5 to 2, and then maybe you can go up and see.
Yeah.
On your cycle there,
yeah.
You can see that the left and the right boundary are about that, and then the bottom and top boundary from here, what is it, like 1 to almost to 3? So if you go back to your
3, and then you go back there, and it's something like 1
to a little more than 3, yeah. So
actually, one thing you could do is, instead of plotting all of these trajectories, you could take one single trajectory and run it for a long time and discard the initial piece of the trajectory, and then you should see it just looping around this periodic cycle in the plane, which is called a limit cycle. So it's a cycle because it's periodic, and it's a limit cycle because everything converges to it. So that is a new type of behavior that we could not see in one-dimensional systems, and is very common to see in two-dimensional systems. And where does it come from? It comes from this bifurcation that happened at some particular value of b. This fixed point here was stable and became unstable. That's that can also happen in one dimension. You can have a fixed point that changes from being unstable to stable to unstable. But in two dimensions, when that happens in a particular way, it can actually create this periodic orbit around it that's attracting. That's called a Hopf bifurcation. So that's, so here, this is, I changed the parameters, and now this is before the Hopf bifurcation. So everything, starts off sort of oscillating, but the oscillations are damped, and it actually converges to this fixed point. But as I increase b past the bifurcation point, there's actually an exact formula in this particular model for the relationship between b and a that gives this bifurcation point. I don't remember what the formula is. Then you end up with these oscillations instead for that value of b after the bifurcation. So you can actually investigate these systems very nicely using these computational tools, even if you're there are, as I said, there are sort of analytical techniques to do this which sometimes work, but the numerical tools are pretty powerful. Okay, and so finally we get to modeling the weather. So this is a very famous system of equations, the Lorentz Equations, which were first studied by Edward Lorentz, who was a meteorologist at MIT, and he published this in 1963.
I didn't know he was at MIT. We don't have a meteorologist.
Yeah, he was a professor in what is now EAPS, Earth and Physical. What's it called? Earth, Atmosphere, and something. Yeah, but
Earth, Atmospheric, and Planetary Sciences.
Thank you. Yeah. So there are people there studying the atmosphere, studying the ocean, and etc. And doing these climate models, etc. And he was interested exactly in numerical weather prediction, and he ended up with this system of equations. So where does this system of equations come from? it actually models a two-dimensional layer of fluid. So you can think of heating water in a saucepan. And before it boils, so you're heating it from below and it's being cooled from above. And before it boils, you might end up getting a phenomenon called convection, where the hot water from below wants to rise and the cold water wants to fall. And so you end up getting these nice convection rolls inside the water. Of course, it's difficult to visualize that in water. You can visualize it better if you use some kind of oil. And this is called Rayleigh-Benard convection. And you can make a you can make a model of that as a partial differential equation. So you have this fluid moving in space and time, and you have and the temperature of the fluid is important. Different pieces of the fluid have different temperatures. So it's actually a pretty complicated partial differential equation. And he wanted to simulate that on a computer. The computer that he was using was actually an analog computer. It was not a digital computer. So he had sort of physical resistors and things modeling this set of differential equations. And so this set of ordinary differential equations actually comes out of that set of partial differential equations when you do some kind of expansion where you represent the quantities occurring in the partial differential equation in terms of Fourier series and things like that. And then these x, y, and z are actually the amplitudes, the size, the magnitudes of each of those Fourier coefficients. And this is the sort of simplest possible version of that model where you only keep the bottom three of these coefficients. There are more complicated versions of this model where you keep more of the coefficients, which you can look up, of course, in the usual place. By which I mean Wikipedia, which is, the embodiment of this 17th century or 18th century ideal of an encyclopedia of all human knowledge. It's a pretty amazing achievement that we should recognize more, in my opinion. Anyway, so he reduced everything to this set of three ordinary differential equations, which are coupled, right? The dynamics of x depends on the value right now of y and x. The dynamics of y depends on z, x, and y. And the dynamics of z depends on x and y and z as well. So they're all coupled. You have to solve them all together, but they look pretty simple, right? They're almost, they look almost so. And then sigma, rho, and beta, are parameters as well. We're representing, various physical quantities like how fast heat transfers through the fluid, etc. So you can look up all of the details as well on Wikipedia, for example. So this looks like a very simple system of equations. And, at the time, people thought that differential equations behaved in a nice way, let's say, roughly speaking. And, the only difficulty about these differential equations is that there are two nonlinear terms, so x times z and x times y. But apart from that, they look pretty innocent. But it turns out that they are very far from being innocent. And this was, a major discovery that was one of the foundations of what is now called chaos theory, which is sort of a thing that mainly only exists in popular science books in some sense. I mean, it's a sub-part of the dynamical systems on nonlinear dynamics. So let's write down the Lorentz equation function to put into differential equations.jl and solve it just like we did last time. Here are the parameters we're going to use. These values of sigma equals 10 and rho and beta equals 8/3 come straight from Lorentz's original paper. And then there's this other parameter rho that we're going to change. So here's what the dynamics looks like. We're starting close to the origin, close to 0, 0, 0. If we start exactly at 0, 0, 0, we'll stay there because it's a fixed point. We're going to start close to it, and we see that we move away, so it's an unstable fixed point. And this is a picture in 3 dimensions of x, y, and z.
I bet you Lorentz did it on punch cards and maybe couldn't even visualize it, I suppose.
Yeah, that's not sure exactly. Yeah, there's various stories about it that you can look up. But as I said, it was actually an analog computer. So he actually had dials that changed some kind of resistances or something. He didn't have punch cards. He literally had dials that he could change to set these parameters. But then he had some kind of output which printed out the numbers. And then he wanted to, so he did have some way of putting the numbers back in. That's true. I'm not sure. Anyway, so what is this particular trajectory for this particular value of rho? It leaves the origin, it moves away from this fixed point, and it spirals into another fixed point, right? You can see that it's spiraling into something, and that something has to be a fixed point. But then as I change rho, hopefully this will work, I'm going to increase rho. At some point, this fixed point, well, at some point something happens. So what happens? So unfortunately, it's been quite slow. I'm not sure why that's happening. At some point, for some particular value of rho, what happens is that this trajectory that was spiraling actually comes back and hits this fixed point again. And then for values of rho bigger than that, you can see that the trajectory sort of misses the fixed point at 0, 0, 0 and goes and spirals into this other fixed point over here. So it sort of qualitatively changes where it's going to. And there's actually, if you go off the other direction, it will spiral into this fixed point. And so they kind of swapped over direction, swapped over where they're going to. That's a kind of bifurcation. It's actually a global bifurcation, I believe, because it's to do with this whole structure hitting something else. It's not a local change of stability. Anyway, as I increase the value of rho more, you can see that I'm spiraling into this fixed point, and I can spiral in more and more slowly, and eventually that fixed point actually becomes unstable. And now my computer has just seized up. Oh dear. I'm apparently demanding too much of it. I don't know what's going on. I can't move anything right now. Oh dear. Oh, there we go. Okay.
While you're getting back, I was just starting to read Wikipedia, and it looks like the original computations were done by a couple of women, which was not unusual at the time. That many of the original folks who were doing computations were staff, often of women. I heard about this at MIT.
But unfortunately, they did not get credit on the publications.
But there were, it did say that Lorentz did give credit.
Well, he gave an acknowledgement.
An acknowledgement. Maybe that's not the same thing as credit.
I mean, they weren't co-authors, is what I mean. So, okay, there we go. So it's spiraling in more and more slowly, and then at some point, which I'm not going to be able to find exactly, that fixed point actually becomes unstable, and then this happens. Suddenly, you give rise to this completely new kind of behavior, and you've probably seen this picture before. This is the Lorentz Attractor. So basically, most initial conditions in the three-dimensional space are actually attracted to this object, and this object lives in 3 dimensions. These two kind of wings are actually at an angle. If you rotate around in 3D, maybe I can try and do that with Plotly. I'll do it in a minute. And so this is actually an object that is a fractal. If you zoom in on these kind of pieces, you'll see that they have finer and finer structure as you zoom in. And this object has 0 volume in 3 dimensions, but it has a fractal dimension, which is bigger than 2, whatever that means. So it's sort of saying that it's more than 2-dimensional, but less than 3-dimensional in some sense. And the key point is that the dynamics in this system is now chaotic. So what do we mean by chaotic? It has a very special, very precise technical definition in this context, which is that 2 initial conditions that start close together will spread apart, will sort of split apart exponentially fast in time. So I actually did that calculation. So I'm taking an initial condition, that calculation was with initial condition 0.01, 0.01, 0.01, and now I'm taking a different initial condition, which is the same one, but perturbed by epsilon in each direction, where epsilon is 10 to the minus 10. So it's, very, very small number. And then I'm going to solve both of those for both of those trajectories, just using differential equations JL, and calculate the distance between them in the 3-dimensional space. And this is the result. This is a semi-logarithmic graph. So this is logarithmic on the y-axis. And what we're seeing is basically after some time, we have this basically straight line on this graph. And that means that I have exponential growth in the distance between these trajectories. That is exactly the hallmark of chaos. deterministic chaos. Until something happens, which is that, oh, this object has a finite size. And so, I can never get a distance between these points, which is bigger than sort of the diameter of this object. And that's what we're seeing here. So it saturates again, because now they're just moving around on this object, on this attractor, and they're some distance apart on average. But you can see that, this is the sort of simplest way to see that, oh, this dynamics is actually chaotic, and you get this really fast separation of two initial conditions that start close together. So here's another visualization of that. This is just the x component of the position. You can see that they start, very, very close together, and they follow each other exactly. You can't even see both the curves. They're right on top of each other for a pretty long time, actually. And then here they just start to, but the distance between them we know is growing exponentially. You just can't see it on this graph. But then here you can see that you can see visually what's happened, that they're separating, and eventually they just start doing completely different things. They're basically going around this attractor a different number of times in different ways at different moments. And finally, okay, and so that is deterministic chaos. And so that means that the weather is unpredictable, right? If this is a model of the weather, this is a model of the atmosphere being heated and cooled and whatever, then after some time, so there's some time during which I can predict the weather, and then after that, it just all goes horribly wrong, and I can't predict anything. But what about the climate? So what is the climate in this context? It's actually some kind of average weather, right? So you can ask the question, what is the average, say, position over time, averaged over a long trajectory, a long time? So I also did that calculation. So I'm starting from a different position, whatever, but then I'm taking a much longer trajectory, 1,000 times, time 1,000, and I'm averaging the absolute value of the x, y, and z components for each of these two trajectories. So these two trajectories are doing completely different things in space, but you can see that the averages over this quantity are pretty close together. And so basically you can think that the average is just a property of this whole system. It's not a property of the individual trajectories. And so that's like saying that we can predict the climate even though we can't predict the weather. Okay, so hopefully, just to summarize, we've seen that simple models of physical systems can exhibit different types of behavior. They can converge to fixed points, they can converge to limit cycles, these periodic orbits, and they can have chaotic behavior. And in general, sort of as a general rule, you can expect a set of 3 or more nonlinear differential equations to have chaos in some part of phase space. I don't think there's a theorem that says that, but sort of in general, you can expect that.
So maybe just one last takeaway that kind of just emphasizes what David's saying. Some people, like, I don't know, some climate denial people or whatever, I've heard people say, if the weather is chaotic, how can we possibly predict, the climate 20 years from now? And now we see from this model that, exactly what Dave just showed, that in fact, that we very much can predict the climate, even if we can't predict the weather, right? Because it's the averages that are going to matter and not the individual characteristics.
Yeah, exactly. So so in the next few lectures, we'll be delving into more details of actual models of the climate and see how these ideas can be used there. Okay, thanks everybody. So see you on Monday. Bye.